afternoon everyone. Today we are here to learn about binary search tree. A binary search tree is a finite set of one or more nodes such that there is special designated node called root. The root is divided into two children, left node and right node, T1 and T2. There are operations in binary search tree: insertion, deletion and also search. Insertion refers to adding an element into the BST. Deletion refers to deleting an element from the already assigned binary search tree. Let us learn about leaf node. A leaf node is a node with no children. Here in this BST, 1, 4, 8 are leaf nodes. 6 refers to root. 3 and 7 are children of root 6. Let us learn about binary search trees insertion operations. We have taken a few elements like 50, 30, 70, 20, 40, 60 and 80. Here 50 is the first element, so it is the root node. The second element we have taken is 30. 30 is less than 50, so it stores in the left subtree of 50. Now we compare 70 with the root node 50. 70 is greater than 50, so it stores in the right subtree of 50. So here 20 is less than 30, so it stores in the left subtree of 30. Next 40. When we compare 40 with root node, it is less than 40. So we will compare next 40 with 30. 40 is greater than 30, so it stores in the right subtree of 30. Hereafter the element is 60. 60 is greater than the root node 50. So we compare it with 70. When we compare 60 with 70, 60 is less than 70. So it stores in the left subtree of 70. So here 20 is less than 30. So it stores in the left subtree of 30. Next 40. When we compare 40 with root node, it is less than 40. So we will compare next 40 with 30. 40 is greater than 30. So it stores in the right subtree of 30. Hereafter the element is 60. 60 is greater than the root node 50. So we compare it with 70. When we compare 60 with 70, 60 is less than 70. So it stores in the left subtree of 70. Our last element 80. When we compare 80 with 50, 80 is greater than 50. So we again compare 80 with 70. 80 is greater than 70. So it stores in the right subtree of 70. This is how we do our insertion in binary search tree. Let us learn about deletion. So let us learn about deletions from binary search tree. There are three types of deletions in binary search tree. If deleting element or key is a leaf node, then we can directly delete the key from the BST. If we are trying to delete a leaf node, then we can delete it directly. For example, let us see this binary search tree where I want to delete 80. 80 is a leaf node. So I can delete it directly. After deletion, the tree will be something like this. So this is deleting leaf node from binary search tree. But when it comes to one child, a key that having one child, we need to connect the child to directly the node. If we want to delete 20 from this tree, then 25 will be directly connected to 30. The binary search tree will be something like this. 25 will be directly connected to 30. So the third type of deletion in binary search tree is if the deleting element or key have two children, then we will replace the key element with in-order successor or in-order predecessor. Let us see an example to understand it better. Here I want to delete 65. So it has two children. Now if I want to delete 65, 65 will be replaced with in-order predecessor or in-order successor. That means the maximum value of a left subtree or minimum value of right subtree. Here the tree comes like this. This is the subtree if we follow in-order predecessor. 64 is the highest value in left subtree. This is deletion with in-order predecessor. So let us see how the BST will be when we do it with the in-order successor. Now we need to delete 65. The least value in right subtree is 70. So now we replace 65 with 70. This is deletion with in-order successor.
Now, we will check whether the node is a leaf node or not. To determine whether a node in a BST is a leaf node, you need to check if both its left and right child nodes are none. A leaf node is a node that does not have any children. Let me explain it clearly. We will take an example of a binary search tree 50, 30, 25, 70, 60 and 40. Here 50 have right child and left child, 30 and 70. Also 30 have 25 and 40 as their children, 70 have a children 60. But 25, 40, 60 does not have any children. So the 25, 40, 60 elements are considered as leaf nodes. Now let us discuss the code to check whether the node is a leaf node or not. The init method initializes a node with a value key and sets its left and right children to none. Here, isLeaf is a standalone function that takes a single argument node. It returns a boolean value whether the leaf node is a true or false. Specifically, the function evaluates whether both the left and right attributes of the node are none. If both are none, the node is considered a leaf node and the function returns true, otherwise false. Now, let us find the minimum and maximum element of any node in the tree. To find the minimum and maximum element of any node in a binary search tree, we typically look for the in-order predecessor and in-order successor of the tree. Key concepts: in-order predecessor, the maximum element in the left subtree of a given node. In-order successor, the minimum element in the right subtree of a given node. Let me give you an example. Now to find the in-order predecessor in this current tree, we will take the root node 15 and move to the left subtree. Left subtree element, first element is 10. In this left subtree, we have to find the greatest element, as the in-order predecessor defines as the maximum element in this left subtree. The greatest element will be the 12, so the 12 element will be the in-order predecessor. And to find the in-order successor, we move to the right subtree of the given tree, and in the right subtree, the first element is 20, and from 20 we have to find the minimum element in the tree. The minimum element is 17, so 17 will be the in-order successor. Let me explain the code to find the maximum and minimum element of any node in the tree. Here we used init method to initialize self.left to none and self.right to none and self.value to the key. And to find the maximum element, which is in-order successor, to find the in-order successor of any node, we move to the right child and then keep moving to the leftmost child in the subtree. As current is initialized to the node, which means root.right, while current.right is not none, we will iterate.
Now let us learn about the level of any node in BST. The level of a node is the number of edges on the path from the root node of the node itself. The root node is at level 0. Now let us discuss about the code. If root is none, this means the function has reached a leaf node and the key was not found in the tree. Thus it returns -1, indicating the key is not present in the tree. If the current node's value matches the key, the function returns the level at which the node was found. The function first recursively searches the left subtree by calling itself with root left and increasing the level by 1. The result is stored in variable L. If L is not -1, it means the key was found at the left subtree and the function returns the level L where the key was found. If the key was not found in the left subtree, L is equal to -1, the function then recursively searches the right subtree by calling itself with root right and increasing the level by 1.